Ahead and we're going to look at the real number systems. So pretty much everything we think of as a number falls under the category of real numbers. Okay. The only thing that doesn't fall under that category is something called imaginary numbers, and we're not going to talk about them just yet. We'll talk about them in the end of the third quarter, fourth quarter, around in that time frame. And they're the only thing that falls outside of like the set of real numbers. So pretty much everything else you think of everything you think of as a number falls in that category. And everything that we talk about from now until we get to imaginary numbers is a real number. So real numbers encompass this big overarching all of the numbers that we think of like as numbers. And so our real numbers, we use the symbol R with a double line at the back to denote all real numbers. That right there means all real numbers. If you see that R with a double line at the back, it just means all real numbers. And then we have real numbers get split into two more categories. So we're going to first talk about irrational. Okay, so there is a very, very common irrational number that you use in geometry when you're dealing with circles. Does anybody know what that is? Pi. Why is pi irrational? What does it do that makes it irrational?
It continues on and on.
Yeah, it goes on and on forever. Okay, so whenever we're talking about the irrational numbers, we are talking about numbers that have decimals that never end. Okay, we can also consider it to be irrational if it never ends and it has no repeating patterns. Okay, so like if it was 5.3 repeating, like so 5.3333333333333, because we can write that as just 5.3 with a little, because we can denote that as something smaller, that's not irrational because that pattern repeats forever. Okay, if it has no repeating pattern and it goes on forever, that is our irrational numbers. Okay, and when we look at irrational numbers, a lot of times you will see an I used to denote that. Thank you so much. And so we have, and the I has double bars, but if y'all want to just write a normal I, I'm okay with that because sometimes when we write the double bars, when we're like writing it out, it ends up looking like a Roman numeral 2, and that just looks weird. So if you just want to do a normal I, that's fine. But it does technically have the double lines in it. But the most common irrational number that we think of is pi. Okay, once we have pi, there's a few other things that end up being irrational. So in order for something to be irrational, it has to be something that creates the decimal that never ends, right? So the things that most commonly create that are if you take the square root of a number that doesn't have the perfect square. So like for instance, let's see. If I was to do the square root of 2, okay, so the square root of 2 is 1.41421356, and it'll keep going, right? Even the calculator around somewhere. So that makes it we can't write that out without rounding somewhere. So that makes it an irrational number, okay? What's another number we could take the square root of and it give us an irrational number? What's a number that doesn't have a square root? 5, yeah. So if we have the square root of 5, that's also going to give us an irrational number because our square root of 5 is 2.236067978. It is 767 in there. Okay, but that is our irrational numbers. Remind me your name, sweetie. All right. Now, we also have, if it's not irrational, that means it's going to be rational. So if irrational is a decimal that never ends, what do you think it means to be rational? The decimal ends. Okay, so when we think of a rational number, that encompasses all of our fractions and it also includes decimals that end. So every single number that's a fraction is included in the rational numbers, okay? And so what we're going to do is for the symbol for this one, we've already used R, because R means real numbers, right? So this one is a little different. This one for our rational numbers is Q. And examples of our rational numbers can be 2/3, 5, because both of those can be written as a fraction. So like right now, 5 is not written as a fraction, but if I wanted to write it as a fraction, could I? How? Put it over 1 and all of a sudden it's a fraction. So that makes it a rational number. If it can be written as a fraction, it is rational. We can also do 0.75. Could I write that as a fraction? What? 3/4. Okay. We can also do negative numbers. So like -8 is a rational number. So those are all examples of our rational numbers. Okay. Now, from here on out, it's kind of like one of those Russian nesting dolls. You know those dolls that when you open it, there's a smaller doll inside, and then you open that, and there's another doll, and then you open that, there's another doll. So every one of these, so our real numbers encompasses all of them, right? Then the real numbers get split into irrational and rational. But our rational numbers keep breaking down into smaller and smaller chunks of them. Those chunks are called subsets, okay? So each of these chunks is going to include less and less numbers. So our rational numbers includes our fractions, our decimals, everything, right? Now, integers, which we use Z with a double line in it for. Remind me your name, please. But our integers are our number line numbers, okay? So those are the numbers that we think of that are like on any number line, right? So like it's all of these numbers and includes infinitely both directions. So what we're going to do to show that it goes both directions forever is we're going to put dot, dot, dot. And then we're going to do -2, comma, -1, 0, 1, 2, comma, dot, dot, dot. For it to be an integer, it is going to be specifically those numbers that are mentioned on your number lines. It will not include decimals. It will not include fractions, okay? It will take those out and just be the numbers on the number line. Now, that goes a next step further to our whole numbers, which we use W for. Now, I like to think of whole numbers as our counting numbers. So these are the numbers you use when counting things or objects. So for instance, how many watermelons do I have right now? 0 watermelons, right? Okay, can I have negative watermelons? No, because I either have a watermelon or I don't, right? So when we count with things, that's where we use our whole numbers. So these start with 0 and go up. And it will go up forever. But we're just going to go 0, 1, 2, dot, dot, dot. Because y'all have no idea. At home, I could have 67 watermelons. Okay? I could be one of those wackadoodles in the math word problems, right? That have a ridiculous number of random fruit for absolutely no reason. You can't eat that many watermelons. But you don't know. But that's what it means to be a whole number. It's the numbers you got count objects with. That's why it starts at 0, because you can have 0 of an object or you can have 200, okay? Now, that gets narrowed down even further when we talk about our natural numbers. And so we use an N with a little double line right there for our natural numbers. So the reason it's called the natural numbers is because math has evolved and things have added to it over the years, right? But in the earliest forms of math, these are the only numbers we had. It took a very long time for 0 to be accepted as a number, for even fractions to be accepted as a number, decimals. All of those things came in steps with math. What we started with, though, is 1, 2, and 3, 4, 5, 6, 7. So your natural numbers is just 1 and up. So each of these subsets gets more and more specific, right? Until we have just our positive numbers. And as we are looking at this, it's less, we're going to name the subsets which all of these numbers below belong to. But it's less about us being able to go, oh, that's a natural number, oh, that's an integer, and more about us being able to recognize when we hear the word integer what that means. When we hear that it's rational, what that means. And knowing that, oh, that means it's going to be a fraction. Oh, we're going to have, if it's all the whole numbers, can it be negative? No. Okay. If it's the natural numbers, can it be 0? No. Okay. So it's being able to recognize those things and recognize the words. So what we're going to do is we're going to go ahead and we're going to name the subsets each one of these belong to. So is 25 a real number?
Yes.
Is 25 rational or irrational? It is rational. Okay. Is 25 an integer?
Yes.
Is 25 a whole number?
Yes.
Is 25 a natural number?
Yes.
Okay, so it fits into all of the subsets, from real all the way down to natural. The only one it doesn't fit in is irrational. Okay, so for number 2, we have negative 12. Is negative 12 a real number?
Yes.
Is negative 12 rational or irrational? Rational. Okay, is negative 12 an integer?
Yes.
Because negative 12 is included on our number line. Is negative 12 a whole number?
No.
And if it's not a whole number, can it be a natural number?
No.
No. Okay, so that just belongs to the subsets real, rational, and integer. Okay, for number 3, we have 3/7. Is that a real number? Now, is that rational or irrational? Why do we know that's rational? Because it's a fraction. Okay, if you see a fraction, you automatically go, that is a rational number. Okay, now, is that an integer?
No.
Okay, so if it's not an integer, can it be a whole number?
No.
Is it a natural number? Mm-mm. All right, so it is just real and rational. Okay, now for number 4, we have the square root of 21. Is 21 a perfect square?
No.
Can I take the square root of 21? Well, I'll tell you what it is. Let's see. It is 4.582575695. So, is that a real number? It is a real number, yeah. Is that rational or irrational? Irrational. So if it is irrational, can it be any of the other sets? No. Because in order for it to be any of these, it has to first be a rational number. All right, for number 5, we have 0. Is 0 a real number? Okay. Is 0 rational or irrational? Is 0 an integer? Is 0 a whole number? Is 0 natural? No. All right, for number 6, we have negative square root of 16. Well, first, what is the square root of 16? 4. So this is actually just negative 4. So is negative 4 a real number? Is -4 rational or irrational? Is that an integer? Is it whole? No, because can we have -4 watermelons? Okay, is it a natural number? So what I want y'all to do real quick is I want y'all to do 7, 8, 9 for me. And I'm going to go run and start the copy machine. I've been waiting for it all morning. All right. So for number 7, we have 6 over 3. What is 6 divided by 3? Okay, so is 2 a real number? Is 2 a rational or irrational number? Is 2 a integer? Is 2 a whole number? Is 2 a natural number? Okay. For number 8, we have pi. Is pi real? Is pi rational or irrational? So is it anything else? Okay, for number 9, we have 5.3. Is that a real number? Is that rational or irrational? So even though that's a decimal, it can be rational? Why is it rational and not irrational? Because it ends. But is it an integer? So is it anything else? All right. For number 10, let's see if we can uncomplicate this a little bit. What is the square root of 81? So we have 9 divided by -3, which is -3. Is that a real number? Okay. Is that a rational number? Is that an integer? Is it anything else? All right, for number 11, is -2.875 real? Is it rational or irrational? Rational, because it again ends. And technically, 0.875 is 7/8. All right, is it an integer though? No. Is it whole? Is it natural? All right, for number 12, can we take the square root of 21? Okay, so the square root of 21 by itself is just irrational, right? Well, what is anything divided by itself? So the square root of 21 divided by the square root of 21 is just 1. Is 1 a real number? Is 1 rational or irrational? Does it belong to anything else? What? Everything. It is an integer, it's a whole number, and it's a natural number. Okay, so that is our number systems. Just being able to recognize when a number belongs to what number system is very useful. Okay. So now what we're going to do is we're going to go ahead and we're going to talk about operations. Okay. So in math class, if I say we're going to do operations today, does that mean we're picking up a scalpel and cutting somebody open? No. Okay. It means we are adding, subtracting, multiplying, and dividing. Okay. Those are our core base arithmetic operations that we use throughout everything. We just add other things with them. So we're going to start with these because one of the most common mistakes made in not just Algebra 1, but basically most math classes in high school is mistakes with negative numbers. Okay, negative numbers account for like half of the mistakes that'll happen in this class. Just because it's really easy to miss a sign. And so we're going to just take a second to make sure we got this. And then we're going to look at, or briefly talk about the order of operations today too. So for number 1, we have -7 plus -4. What is that? Is what? -11. Okay. We could also have just said -7 minus 4. That would have also worked. Either of those things mean the same thing though. So now we're going to look at number 2. What is -2 minus 5? -7, okay? Because we have -2. We're already at -2, and then it goes back 5 more. All right. For number 3, what is 3 minus -2? That's weird. How did it become 5? So that is technically 3 plus 2, because when we have a negative and a negative, it makes it positive. Well, I have a question. Why did these two negatives make it positive, but these two didn't? In order for it to make the two negatives positive, the negatives have to be next to each other, right? Here, we're saying -2 minus 5. Okay, and so it's making it's separating those negatives, right? But when those negatives are side by side like that, that's what makes it positive. What about 5 minus 5? Okay, now, in order to add or subtract fractions, you have to have what? Common denominators. Do these have common denominators? No, right? Because one's got a 2 down here and one's got a 4. So is it easier to make a 2 into a 4 or a 4 into a 2? What do I need to multiply 2 by to get that? 2. When I multiply this by 2, do I just multiply the denominator? What do I multiply by? Both, right? So you actually do 2 over 2. And the reason we do that is because what is 2 divided by 2? It's just a fancy way of multiplying by 1. So now, 2 times 1 is? 2 times 2 is? Is 2/4 and 1/2 the same thing? So we're just making these two things equivalent, just with a different denominator, okay? And then do I need to do anything to minus 7/4? So we'll bring that down. So if we subtract that, do I subtract the numerators, the denominators, or both? Just the numerators. So what are we going to get when we can say 2/4 minus 7/4? -5/4. Okay, and we will leave our answer written as an improper fraction. We will never, ever convert to mixed numbers in here. Okay, we will just never do it. Okay, now, we're going to go ahead and look at number 6. So, in number 6, do we have common denominators? Okay, so let's go ahead and look at this. What is -5/6 plus 3/6? -2/6. Can I simplify that to what? -1/3. And that is our answer. Also in here, if we can simplify, we will every single time. Okay? We will always write it in simplest form. Also, I'm so sorry about that. I just keep missing the copy machine. There keeps being people at it, and so I'm having to make them on here, and it's noisy, and I'm so sorry. But now we're going to talk about multiplication and division. What is negative 10 times negative 3? Positive 30, because a negative times a negative is a positive. All right, now for number 8, what is 8 times 6? All right, for number 9, in order to multiply with fractions, I want both of them to be fractions. It makes it easier. So what can I do to make 5 a fraction? Now, when I multiply with fractions, I multiply straight across. So what is 7 times 5? And then 4 times 1 is? And is that something that we can simplify? Can anything go into both 35 and 4? So that right there is just our answer. All right, for number 10, we have a negative times a negative, which is going to make our answer. And then we have 7 times 8, which is 56. And we have 5 times 4, which is... Now, can I simplify that? What can go into both 56 and 20? Not 5, a little bit smaller than 5. 4. Okay? So what we do to simplify this is we just divide both things by the biggest common divisor, right? So we're going to do 56 divided by 4, which is what? It's not 8. It's 14. Okay, then we do 20 divided by 4, which is... Can I simplify 14/5 anymore? Now, if you did not see that and think 4, that's okay. You can also do it in steps. If you would have said, oh, both of those are divisible by 2. What is 56 divided by 2? 28. What is 20 divided by 2? 10. But could I simplify that even further? By taking out another what? 2. What is 28 divided by 2? What is 10 divided by 2? Okay, in this class, I will never fault you for doing the math a slightly different way than me. Okay, there are multiple ways to do basically every single problem. Okay, what matters is that the steps you are taking are mathematically sound. Okay, so there will be times where I do something using more steps than you did, or vice versa. And so if you're ever doing something and it looks different than what I'm doing, that doesn't mean it's automatically wrong, okay? If you're not sure, if you're getting the same answer as me, and you're like, am I doing this in a way that makes sense mathematically? Ask me. I'll look at it. Because if what you're doing makes sense to you, I want you to keep doing the thing that makes sense to you. So we all have brains that work differently. Just because something makes sense to my brain doesn't automatically make it make sense to yours. I wish it did, because as a teacher, then I would just walk around and going, boop, boop, and just give you the math knowledge, right? If I could do that, I would. But it doesn't work that way, okay? So I want to make it make sense to you, and so to do that, we had to figure out the way that it makes sense in your brain. So if you're doing something and it looks different than me, but you're still getting the right answer, let me look at it. I would love to see you a different way of thinking, okay? Because sometimes it's not the way I've thought about doing it before. Or maybe it is, but I'm like, that feels too complicated. But it makes sense to you, okay? Because I try to pick the way that is the easiest method. But that doesn't mean it's easier to you, okay? When there is multiple methods, I try to show it, but I can't do that for every single problem, or we'd be here all day. Does everybody get that, though? Okay, I just want to make that very clear from the get-go. I'm not going to fault you for doing it a different way to me. But you need to be able to mathematically explain it, okay? And that's a big thing. Number 11. What is 24 divided by 4? Okay. What is 1 divided by negative 1? Okay. Oh, this is weird. So we have 7/4 divided by 3/4. What do you do when you divide by a fraction? Does anybody remember? Yes. Yeah. So what we end up doing is, it's often referred to as keep, change, flip, right? So when we do that, we take what we start with. So in this case, it is 7/4, and that's going to stay the same. Then instead of dividing, we're going to change the sign to multiplication. And then we flip the denominator. What is the mathematical word for flipping a fraction? We're making it into the, starts with an R. Reciprocal. Okay? And so that just means we flip it. Okay? So whenever you divide by a fraction, you multiply by the reciprocal. Okay? So you keep, change, flip. Now we just multiply straight across and simplify. What is 7 times 4? What is 4 times 3? Now, what is the biggest thing that can go into both of those? 4. 28 divided by 4 is? 12 divided by 4 is? So that is our answer in simplest form. Okay? Now, number 14 is the exact same thing. It's just written differently. Okay? So for this one, we have -1 divided by 7. So I'm going to keep, change, flip. So I'm going to keep -1, but I'm going to go ahead and write it as a fraction. How would I write that as a fraction? Over 1. And then I'm going to change my sign. And then I'm going to flip my fraction. So what is it going to become? And if I multiply that all together, what do I get? And can I simplify that any further? Nope. Okay, so that right there is our answer. Now, we are going to real briefly, because we don't have very much time. What is the order of operations? Parentheses. When we say parentheses, we mean what part? Yes. So we have parentheses, exponents, multiplication, division, addition, subtraction. So if we're talking about parentheses, we're talking about what part of the parentheses? The inside, okay? If we're talking about exponents, okay, what does it mean to raise something to the power? So if we say we're multiplying it by itself. When it says multiplication and division, what order do I do that in? Do I do multiplying first, then dividing, or do I go from left to right? Left to right, okay? And addition and subtraction is also going to be left to right. We will pick up there tomorrow.
Everywhere I'm going, I'm only seeing like the notebook version, like the small notebook version.
Like, is it like a binder?
It's like a binder. I don't know because my friend has one. I might just have to ask her.
Can I just look at Office Max maybe?
I think the only thing I'm seeing, I think what it is she just put like.
She made it.
Like she made it where she put, because I'm seeing like these little they call dividers with pockets on them. So maybe that's it, but I didn't know if you knew where it was. So.
Yeah, I don't off the top of my head. I would try. And right now, the school supplies is a little picked over.
Yeah. Well, that's okay. Thank you for helping me though.
I wish I could help more.
Yes, have a good day.
You too. I heard that. She went to
Black. Can't believe it.
what made her decide to do that?
I don't know. She's like, which, understandable, but. Oh, what else?
Back there.
William? I'm sorry. Can we move these desks that way so I can have some backpack space and not have you trip over it?
No. Maybe move your backpack to the front.
Yeah, but then the chair legs get stuck on there. Also, do you want this one?
Did you make it?
Yeah. I think we got it. Somehow.
Yes.
Yes. I don't like the way I did this yellow. My yellow was thick, so I thought it might work. And then it turned out to be way much.
Okay, cool. What's your name? Rogers? All right, so. Let me see where we have. Maybe seat 13? Or seat 13? Yes. Which bus are you? Yes. Bring me your paper and I'll sign it for you. And we're gonna go over today's bell ringer, so don't turn it in as soon as you're done. Okay. Spell your name for me. What's your last name? Hello. Yes, ma'am, this is me.